Welcome back. Today we're going to be introducing Newton's first law specifically, and in the next video we'll tackle on Newton's second law. To start off with a few ideas, Copernicus was an old scientist that ended up figuring out that the Earth revolved around the sun, as did the other planets. Now, as you know, old school thought was heliocentrism, the idea that everything else revolved around the Earth. So his challenge to that and proving it led to new ideas about motion, about orbiting, about gravity, even though it wasn't completely discovered or thought of yet. So it led to a lot of new ideas. So he was very important. Another scientist worth mentioning is Galileo, and this is the guy who basically thought of the idea of inertia. He was the guy who was dropping different spheres off the Leaning Tower of Pisa and figuring out that even though they might have different masses, they basically fall at the same acceleration, which led to the idea that all objects fall at the same acceleration. But anyways, Galileo said that it's not necessary to have a force constantly on an object in order to keep it moving. This was a strange idea because if you roll a ball, eventually it stops. So how could he actually prove that to be true? We'll get into that in just a bit. But first, to quickly mention a few vocab words. When we talk about force, we're talking just about any type of push or pull. And if we're talking about friction, we're really just talking about when two materials move past each other, there is some type of force between them, and we call that friction. When we talk about friction, if friction's present, then you do need a force to keep objects moving. If you could eliminate friction, like in this example, this little gully here, the ball would roll up to the same height and then back and forth over and over again if there was no friction. Though air resistance would be taken into account and eventually would slow it down a little bit, but for the most part that thing would be going for a long time. Also for this one, the ball would roll down and roll up to that height and then back again. Again, only though if there was no friction involved, which we know isn't true in our everyday lives. So Galileo thought, well, if we could have a little hill and no friction, that ball would technically roll forever and ever. And the question is why? Why would it roll forever if there was no friction? And that's where Newton's first law of inertia comes in. The key word here is inertia, which we'll define a little bit better in the next following slides. But Newton's first law states that any object that is at rest wants to stay at rest, and any object that is moving or in motion is going to stay in motion with the same speed unless, big word unless here, we have other unbalanced forces acting on it. So an object not moving wants to just stay not moving, and an object that is moving wants to keep on going. The only reason those would change is because some kind of outside or unbalanced force. To sum that up even quicker, it's basically objects just tend to keep on doing what they're doing. That's Newton's first law. So why is this? Well, objects naturally want to just keep on doing what they're doing. So we could say that they resist change in their state of motion. And this resistance, this idea that they don't want to change, is what we call inertia. So, if you think about it, and this makes sense in our everyday lives, the more massive an object is, the more inertia it has. Think about a car. A car rolling forward wants to keep rolling forward. It's hard to stop it. Like if it was in neutral rolling down a driveway towards you and you got in front of it and tried to push it to stop it, it would take a great amount of force. Why? Because of inertia. Once that car is rolling, it wants to keep on moving. And you trying to stop it is changing its state of motion. If you're trying to change its state of motion, it's going to resist that change. That resistance is inertia. Here's a graphic that might help you for inertia. The ball is at rest, so it wants to stay at rest. Only when an unbalanced force, like a big soccer shoe, kicks it, then that ball starts moving. Now that the ball is in the air moving, it wants to move at a constant speed with a constant direction. But any type of outside unbalanced forces can change that, like it hitting the net, like the wind hitting it and trying to move it, like it hitting the ground and friction acting against it. But either way, it's going to keep on doing what it's doing unless some outside force acts on it. Again, that's inertia, and that's Newton's first law. Now, we said that the more mass you have, the more inertia you have, so it is important to make sure we distinguish between mass and weight. Mass is what actually is the indicator of inertia. The more mass, the more inertia, and we measure mass in kilograms. Don't forget that mass is always constant. No matter where we are in the universe, the mass stays the same. And as we know, the more mass, the more resistance to change in motion, which is just the same way of saying the more inertia. Now, we talked about mass in the previous slide, but weight is quite different. Weight is actually the force due to gravity, and to figure that out, our weight, which we can find out, is just our mass in kilograms times our gravitational pull, which is the acceleration of gravity, which is meters per second squared. So when you multiply those two together, you actually get a unit of newtons, but newtons isn't as obvious when you do the regular equation because it's kilograms times meters per second squared. So newtons is actually a derived term from these units, which comes from mass times the acceleration of gravity. If you take a look at this picture over here to the right real quick, the astronaut's mass is 120 kilograms, whether you're on the Earth or whether you're on the moon. But if you look at their weight on Earth, larger gravitational pull, the astronaut's weight is 1,200 newtons, where the weight on the moon is 200 newtons. Now, I know newtons aren't very obvious to you, so a way you could quickly kind of put things into perspective is, if you got 1,200 newtons, divide it by 4.5, and what that should give you is how many pounds an object is. Now, it's just a way to kind of wrap your head around what we're talking about with newtons here. But try it with the 1,200 newtons, divide it by 4.5, and you'd be surprised. It'll make a lot of sense how much it weighs. It ends up being about 266 pounds. And again, that is totally an estimate, but at least you get an idea of how much this astronaut is weighing. Now, if you do the moon, which is 200 newtons, and divide it by 4.5, you can see that the pounds go down quite a bit as well when it's on the moon. The astronaut only weighs about 44.5 pounds. That's a considerably less amount of force due to gravity. So just something to keep in mind. Weight can change with gravitational pull. Mass cannot. If you took a stack of books on a student's head and you cracked a hammer over it, boom, it actually wouldn't hurt the student. But the question is why? Why wouldn't it hurt the student? Well, the answer is inertia. The fact that the books don't want to move because they're still, and then the hammer tries to move them, those books resist change. And since they're pretty massive, they've got a pretty big mass to them, they really, really are resisting change. So when you crack the hammer over the head, even though the person feels it over their head, it doesn't hurt them because inertia is resisting that change from not moving to moving. And to end everything, last but not least, let's think of inertia in action. If this gentleman right here is on a plane and they're flying through the air at high speeds, why is it that when he flips a coin in the air, instead of it flying behind him into a seat behind him, it actually just comes back down and lands in his hand? You could do that on a bus as well, or while riding a bicycle, anything like that. Why does it actually land back in your hand? Well, as you've caught wind on everything else, the answer is inertia. The fact that the coin is moving at the same speed as you and the airplane means that even though you flick it up in the air, it's still going to be moving forward with your body and the airplane. Again, that's due to inertia. You experience that every time you hit the brakes on a car. Your body flies forward as you brake heavily on a car because your body still wants to move. That's what inertia is. It doesn't want to change, so it wants to keep moving. Same with the coin. And if you take a look at this train wreck of a mess picture right here, this is a semi-trailer that slammed on the brakes, so it had enough force to stop, But this huge, massive limestone right here couldn't stop and actually kept moving forward. Think of it as a really heavy person without a seatbelt. Even though you may have stopped with proper brakes and seatbelts, that person might fly through the windshield. That's what happened here with this semi-truck. It crashed into the cab and actually smashed it. So pretty crazy to think about, but inertia in action there. You have to take into account all those things when you are thinking about inertia. Well, this ends our little presentation on Newton's first law and inertia. Don't forget, we talked about the difference between mass and weight, and of course, the idea that inertia is directly related to the mass.